Hi guys! Today we're going to be talking about the applications of stable and radiogenic isotopes in igneous petrology. So before we jump right into the more complicated stuff, let me just briefly go over some isotope basics because I have a lot of isotope videos on my channel, but if you've just watched the igneous petrology videos so far, you probably haven't seen any of the isotope videos. So let me just recap the important things regarding isotopes, basically what they are and what they mean and why they're helpful to us. So here we have a periodic table, and the periodic table shows all these elements here, and each element is defined by its number of protons. So if the number of protons changes from 6 to something that's not 6, the element is no longer carbon, it is something else. But isotopes are defined by number of neutrons. So if the number of neutrons changes, then the isotope changes, but it's not a different element, it's just a different isotope of that element. For example, there are different isotopes of hydrogen shown here to the right, and we can see that even though hydrogen always has one proton, it does have a changing number of neutrons. And these different variations of hydrogen are all different isotopes of hydrogen. Same thing goes for basically all the other elements. They all have different isotopes of themselves. And something that changes when neutrons are added or taken away from the nucleus of an atom is the mass of that atom. And so since the mass changes, we refer to different isotopic pairs, which we'll go over later, as having a heavy and a light isotope. So we'll talk later about isotope ratios, and there'll always be a heavy isotope and a lighter isotope. The lighter isotope obviously has less neutrons, and the heavier isotope has more neutrons. And quite literally, it actually means that they're lighter and heavier. And because of this, their behavior is different in different situations, which allows us to track their behavior and use that to our advantage when we're measuring those ratios later and understand how different processes happened to form rocks. So that's getting ahead of ourselves. We'll talk about that more as we go through the video. One really important thing about isotopes for this video specifically is that they can either be stable or radioactive. Now, if you guys have seen any of my previous isotope videos, you know that I have talked a lot about stable isotopes. Those are isotopes that do not change, do not decay. They are stable the way they are and they stay the same. However, isotopes can also be radioactive or unstable. These unstable isotopes decay over time. And because of this, the ones that decay are called parent isotopes, and what they decay into are called daughter isotopes. And over time, if you look at this rock over here, we can see that these red dots indicating parent radioactive isotopes decay over time to form these blue dots, which are the stable daughter isotopes formed due to the decay process of the red isotopes. And over time, the red decreases and the blue increases. And this is actually the basis for absolute dating. This is a technique in which we can date rocks or figure out their age by measuring their isotopic abundances. And not only can we use isotopes to figure out rock ages, but we can also use them to identify the sources of their components, for example, what source magmas they came from, and the processes that led to their formation, as well as alteration processes. So we'll talk today about how to use isotopes to figure out all of these different things listed here, but we're going to split it up into two major parts of this video. The first part will talk about how we use stable isotopes in igneous petrology, and the second part will be how we use radioactive isotopes in igneous petrology. First, we need to start with stable isotopes. And like I said, stable isotopes are stable. They do not decay. They like to stay the same over time. So with that, you might wonder, how does measuring stable isotopes really help us determine anything at all if they stay the same over time? Actually, the fact that they stay the same over time is pretty useful because we can measure their ratios with each other to understand how their mass differences affects their behavior. And once we understand this, we can then reconstruct different processes that led to the formation and potentially alteration, etc., of rocks that we are then measuring. So that was a lot of words. Let me break it down. So before we even talk about the applications of stable isotopes, we need to talk a little bit about something called isotopic fractionation. Isotopic fractionation is basically how much the behavior of isotopes of a given element differ from one another. For example, consider oxygen. Oxygen has two major stable isotopes. These are oxygen 18 and 16. Oxygen 18 is the heavy isotope because it has two more neutrons than oxygen 16, and oxygen 16 is the light isotope. So when water molecules evaporate from the ocean, the ones containing lighter oxygen isotopes, more oxygen 16, will evaporate more easily from the ocean than those containing more oxygen 18 or more heavy oxygen. And therefore, the heavy oxygen will preferentially be left over in the solution, and the lighter oxygen will be preferentially incorporated into the clouds above the water. So this is kind of how isotopic fractionation works. There's many different mechanisms that can cause isotopic fractionation, but most of the time it stems from the mass differences due to the changes in the number of neutrons between different isotopes. And now we can see here that two major types of isotopic fractionation exist, and these are kinetic and equilibrium isotopic fractionation. Kinetic isotope fractionation is similar to when we discussed fractional crystallization. We talked about this in the silicate magmas video. I'll link it up here if you want to check it out, but basically what we discussed is how during crystallization in a magma body, so there's chambers of magma in the lithosphere that may start to cool and crystallize, and when they do so, certain materials crystallize out sooner than others, leaving the leftover magma enriched in the things that the crystal doesn't want to take up, which can be a lot of things. I talk about it more in that video. But when we're talking about isotopes, it's pretty simple. Instead of all these different elements that can be compatible and incompatible with the crystals that are crystallizing, we just have to think about heavy and light isotopes. And when we think about this, we can imagine that during fractional crystallization, light isotopes are preferentially incorporated into those early crystallizing crystals, and the heavy isotopes are preferentially left in solution. And that's only because kinetically, lighter isotopes are faster in terms of diffusion, and they will crystallize sooner, and then those heavy isotopes are just slower, and this is all kinetic fractionation. You're going to end up with crystals that are enriched in very light isotopes and solution, or magma in this case, that is enriched in heavy isotopes. But the second type of fractionation listed here is equilibrium fractionation, in which instead of kinetic effects controlling the fractionation, it's more of a chemical equilibrium type of reaction going on. For example, isotope exchange reactions between minerals or between solutions and minerals is common. So if we take an example, which actually will include both types of fractionation to kind of show you how they might work in the same system, we can imagine that the process of ions adsorbing to mineral surfaces, which is really common, can begin with kinetic fractionation, where lighter isotopes diffuse and absorb faster to that surface, causing a discrepancy where lighter isotopes are way more abundant at the mineral surface and the heavier isotopes are left over in solution. And then after the initial absorption occurs, the isotopes undergo exchange reactions until isotopic equilibrium is reached. And so that's kind of how the exchange reactions work, and that shows how kinetic fractionation could occur, and then equilibrium fractionation could kind of take over and overprint the kinetic fractionation, which often occurs in nature. So these are just examples to kind of show you how these fractionation processes work. But when it comes to igneous petrology and understanding the formation and alteration processes that led to the formation of any given igneous rock that you might be looking at, how can stable isotopes and understanding isotope fractionation really help us with that? Well, the good news is stable isotope fractionation is temperature dependent. Because of this, isotope measurements can be super useful when it comes to what's called geothermometry. But fractionation is also dependent on crystallization and assimilation processes, as well as water-rock interactions while the magma is cooling and crystallizing. So isotopes can also serve to trace magmatic processes. But let me just clarify here that I've often referred to reconstructing ancient temperatures using stable isotopes in previous videos, such as the oxygen isotopes video, the sulfur isotopes video, the carbon isotopes video, the strontium isotopes video, the climate video, as well as my oxygen and oxidation event videos. And so I've talked about how to reconstruct these conditions as well as climatic conditions, temperature conditions, all of these things with stable isotopes in these videos. But I want to stress here that when I'm referring to geothermometers in this Igneous Petrology playlist, I'm actually referring more to determining the temperatures of igneous processes that took place for a rock to form. However, after all that buildup, I'm not actually going to be talking too much about geothermometers today. I just wanted to introduce the concept to you guys for when we go over exactly which stable isotopes are great as geothermometers and how to use them, etc., in the metamorphic petrology playlist, because I have a lot to talk about today. And I think for igneous petrology specifically, the radiogenic isotopes that we'll talk about at the end of this video are going to be way more important for this playlist than the stable isotopes. So I'm just going over the concepts of using stable isotopes in igneous petrology, and then we're going to get to radiogenic isotope geochemistry and how that can be a really powerful tool for igneous petrology. One of the ways that it's really awesome is geochronology. You guys probably know what this means because geo means earth and chronology is like dating things or time or whatever. So yeah, it's exactly that. It's understanding how we can date rocks using radiogenic isotopes. And if you are an OG on my channel, you know that I actually have a video all about how we use radiogenic isotopes to absolutely date rocks. And I'm not using absolutely as just a fun adjective here. It's actually the term used when we talk about dating rocks using isotopes. It's called absolute dating. And I talk about this all in that video that's shown right here. I'll link it up here so you can go find it because this is not like a live link or anything. But it's a really old video on my channel. I apologize for the sound or quality. It's not great, but the information in that video is good. So if you want to know more about absolute dating, please go check that out, because in that video, I talk about decay processes. I go step by step through alpha decay, beta capture, as well as I talk about half-lives and how we can use them to calculate the ages of rocks. And I actually go through like 4 different practice problems with you guys at the end of that video. So if you want to learn more about that stuff and get some practice, check out that video, because in this video, we're not going to be talking about that stuff. I'm going to repeat a little bit just to give some background, but we're going to talk mainly about applying absolute dating techniques such as potassium-argon dating, argon-argon dating, which is kind of coupled with potassium-argon dating, and uranium-lead dating. And then we'll also talk about isotopic petrogenesis, which you might not understand that term yet, but we'll talk about that in terms of isotopes such as rubidium and strontium, lutetium and hafnium, and samarium and neodymium. And we'll talk about why those isotopes are really useful in the last part of this video. But first, let's talk about applying potassium-argon dating. So just to briefly recap, we talked about in the absolute dating video, if you went to check it out, great, good job, welcome back. And we talked about in that video how potassium-40 decays into argon-40. Because potassium decays into argon, we can use the relative amounts of these isotopes in a rock to get its age. Just like we showed on the previous slide with the red dots, or the parent isotope, in this case potassium-40, that decreased, revealing a lot of blue dots, or the daughter isotope, in this case argon-40, we can use those abundances to figure out the age of the rock. And we can use this because we know the rate at which potassium decays. That's something called a half-life I discussed in that previous video I mentioned. So something that's important to note is that argon likes to be a gas. This is one of the unique things about potassium-argon decay, is that its daughter product is a noble gas. It doesn't want to be a solid. And so because of this, age estimates could be younger than the actual age of the rock, because we might not be measuring all the argon that should be there because we might have lost some. This is where argon-argon dating comes into play. When using argon-40 to argon-39 measurements, we can actually get around this issue and measure exactly how much argon has been lost, if any. How do we do this? Well, samples are irradiated with neutrons, causing potassium-39, a stable isotope of potassium rather than radioactive, to convert into argon-39. And these irradiated samples are then incrementally heated, and the ratio of argon-40 to argon-39 is measured as these isotopes are released from the rocks during heating. And rocks that have not lost any argon-40 due to diffusion out of the rocks, like I just mentioned, should remain consistent in this ratio across all the incremental heating steps. However, rocks that have lost any argon-40 will show lower ratios of 40 to 39 during the initial lower heating steps, and then later in the higher heating steps, the ratio of argon-40 to 39 will be higher because more of the retentive argon-40 is finally being released. And from this, we can actually determine how much argon had been lost, if any, and estimate a more accurate age of that rock. Another really useful technique for absolute dating is uranium lead dating. This is a very robust technique because two different uranium isotopes, parent uranium isotopes, decay into two different daughter lead isotopes or daughter products. And this means that two different uranium clocks exist in igneous rocks containing uranium that we can then measure and date that rock with. However, you might wonder, well, which rocks contain uranium? Is it really that common? How useful could this be? Well, luckily, accessory minerals such as zircon, as shown here to the right, and monazite, titanite, and apatite contain uranium and can be used to date rocks with uranium lead dating. Additionally, something I mentioned in that absolute dating video is that uranium has a really long half-life, meaning it takes absolutely forever for it to decay into its daughter product. You might think this is a disadvantage, but because rocks are freaking old, it's really useful. And that's because when the half-life is really long, we can date really old rocks. Another great advantage to this technique is that we can even do spot analysis for super precise ages. What does this mean? Well, as we can see, this zircon grain over here has zonation. This just means that it formed in a way that its core is older than the layers on the outside of it. And so because it's layered, we can get a sense for how old the core is, as well as how old the most outer rim is compared to the core. And also, if there's alteration rims, we can get a sense for when the alteration occurred and what types of alteration processes happened, as well as formation processes. And this is all building an amazing picture of the history of formation and alteration of that rock or mineral. Quickly, before we move on to isotopic petrogenesis, there are a few other ways that we can use uranium dating methods, and these include uranium, thorium, helium dating. This method is used to document the cooling history of rocks because helium, one of the decay products of uranium, diffuses out of rocks because, like argon, it likes to be a gas, and because it diffuses out of rocks at relatively low temperatures, it can allow us to document the cooling history of rocks. Another method is called fission track dating because uranium undergoes fission. Because of this, the number of damaged tracks caused by uranium fission can be measured, and because it's a function of age, we can then determine a rough date or age for that rock. Lastly, uranium series dating is using the decay of the intermediate daughter products and their products to determine timescales of geologic processes, such as the generation of the melt and the magma residence times and the crystallization history, and all of those processes can be understood using uranium series dating by looking at all of the intermediate daughter isotopes of uranium, which I don't know if I mentioned this, but I mentioned it in the previous absolute dating video. So if you've seen that, you know I talked about how uranium-238, for example, which is one of the isotopes of uranium that decays, it decays into thorium and then something else and then something else and then something else and like a bunch of other daughter products before it actually gets to the stable lead product, the end product of uranium decay, which is why we can use uranium lead dating. But because there's so many other daughter products that then have their own decay products, we can also use the intermediates and their abundances in the rocks to understand more intricate processes that might have occurred in the magma and rock history, if that makes sense. So That's it for the geochronology section of this video. Now I want to get into how we can use isotopes to determine the source of magma that formed a specific rock and how we can track those sources. But before I do so, I want to acknowledge, because I know I'm going to get some questions out there like, you talked about geochronology, but you didn't mention carbon dating. And the reason I didn't mention carbon dating, just for the record, is because in igneous rocks, carbon dating isn't useful. It doesn't work on igneous rocks. We use mostly on igneous rocks uranium, lead dating, and argon dating. But carbon dating is something that we have to use when there's organic material involved. So sedimentary stuff, not igneous stuff. And I actually talk a lot more about how we can use carbon dating, carbon half-lives, and how far back or how old of rocks we can use carbon dating on in the absolute dating video. So please go check that out if you're interested in carbon dating. But here in this video, this is about igneous rocks and understanding igneous rock formation and processes, not about sedimentary stuff. So now let's discuss isotopic petrogenesis, or studying magmatic sources. In this application of radiogenic isotope geochemistry and igneous petrology, we're actually looking at radiogenic over stable isotope ratios, rather than what we were looking at before, which was parent radioactive isotopes relative to daughter radiogenic isotope ratios. And so instead of looking at parent and daughter radioactive and radiogenic isotopes, now we're looking at radiogenic isotopes, so daughter products of isotopic decay, and stable isotopes. And so isotopes that are really useful for understanding magmatic sources is the strontium 87 to 86 ratios. So strontium 87 forms by rubidium decay, so it's radiogenic daughter product. And strontium 86 is a stable strontium isotope. Same thing goes for hafnium isotopes, which can also be useful. Hafnium 176 forms by lutetium decay, and hafnium 177 is a stable isotope. Likewise, neodymium 143 forms by samarium decay, and neodymium 144 is a stable isotope. And lastly, lead here has 3 different radiogenic isotopes that can be used in ratio to lead 204, which is a stable lead isotope. So because these pairs have radiogenic isotopes over stable isotopes, one of those values will change over time, the radiogenic one. That one will increase through time because it's a daughter product. So over time, more of it accumulates as the decay of whatever its radioactive isotope is occurs. And then the stable isotope in the denominator of these ratios will always stay the same. These types of isotope ratios are really useful because, for example, strontium 87 to 86 ratios are higher consistently in continental crust than they are in mantle rocks. And because of this, rocks with higher strontium 87 to 86 ratios can be determined to be from a continental crust source magma rather than a mantle source. So this means that strontium 87 to 86 ratios can tell us whether the magmatic source was crustal or from the mantle. Not only can it tell us this, but if it is crustal, it can even distinguish whether it was a lower crust source or an upper crust source. I actually discussed the exact values of strontium 87 to 86 ratios in continental crust versus mantle rocks in my strontium isotopes video. I swear my videos are normally not just constant plugs of my other videos, but because this one is an isotope video, it's really repetitive because I have a lot of isotope videos. So I'm just constantly plugging myself, and I'm sorry for that. But I promise you, if you want more information, go check out the strontium isotope video. I talk about the continental crust and mantle rock strontium ratios, how they differ, and how we can actually use that like quantitatively. I talk about numbers there in that video, as well as what's called the 706 line. It's actually here in the thumbnail. You can see the 706 line, and I talk about that, what it means, how we can use it, how strontium relates to that in that video. So go check that out. Again, I'm sorry, but it's out there. So regarding the other isotopes though that I mentioned for understanding magmatic sources, we can also use neodymium and hafnium ratios, and these isotopic ratios have an opposite trend to that of strontium, meaning that instead of being higher in continental crust and lower in mantle, they are higher in the mantle and lower and less versatile in the crust. Well, what does this mean? Well, it just means that they're more useful for determining and distinguishing between mantle sources than they are for crustal sources. So just like strontium can be really specific when distinguishing crustal sources between lower and upper crust, hafnium and neodymium can be useful for distinguishing mantle sources. And because of this difference between strontium and neodymium and hafnium, we can actually combine those proxies to really paint a great picture of what sources contributed to a magma that then contributed to the resulting rocks that we are then measuring. So guys, that is it for this video. I hope this was helpful for you. If not, I hope the other videos that I mentioned were helpful for you. And my upcoming videos on this Igneous Petrology playlist include the basalt and mantle video, as well as the ocean magmatism video, which neither of those topics I've ever discussed on this channel. So you can expect much more deep and informative videos on those topics, I promise. And lastly, my reference for this video was The Essentials of Igneous and Metamorphic Petrology by Ronald and Carol Frost. And you can check out this book if you want to in my description down below. It's linked down there if you want to check it out for yourself. And again, guys, thanks so much for watching. I hope this video was somewhat helpful for you. And if you have any topic suggestions for Igneous Petrology or any other playlists on my channel, you can comment them down below and I'd be happy to look into those and potentially make a video for your suggested topic. So that's all I got. Thanks, guys. I'll see you next time.